So today's speaker is Kazutoshi Yamazaki. He got PhD from Princeton 2009, and now he's back in Japan, Kansai University. He'll be talking about non-zero-sum optimal stopping game with continuous versus periodic observations. Now screen is yours, please.
All right, so thank you very much. So I'm going to talk about non-zero-sum optimal stopping game with between two players. So this is a joint work with Jose Luis Perez from CMAT Mexico and Neophytos Rododinas from Queen Mary University of London. So so this is the setting. So we start with two players. Let's call like one player P and the other C. So these two players are trying to buy the same asset, but there's only one item. So whoever decides to buy so gets the asset, but otherwise he gets nothing. So this is going to be optimal stopping game because the players try to find the best time to stop, but the payoff is going to be dependent on what the opponent does. So the new feature of this talk is that one of the players, so player C, so gets to observe the asset, so asset value, more often than player P. And in return, player C needs to pay some fee for this additional information he gets. And so also these two players aim to maximize their own payoffs. So if you sum up the two payoffs, so that sum is not going to become zero. So that's why so this is going to be non-zero sum game. Okay, so let me repeat using a bit of notations. So we start with continuous time Markov process X. So we call X the state process. And so for player C, we just assume that so he can observe the process X in a usual way. So we assume that so C can observe X continuously, and and also can exercise at any time. So for player C, it is almost the usual optimal stopping problem. Except that there's an opponent and his payoff function. So payoff depends on the opponent's strategy. And so I'm going to use FC for the payoff function for player C. And so this is dependent on the asset, the state process X at the time he exercises. And he gets this payoff only if he stops before the player P. Okay, so about player P, so P stands for periodic. And so here, so he only has limited access to the information. So we assume that player P, can observe the process X only at independent personal arrival times, whose rate is given by lambda. So basically at each time, so player P has to wait for independent exponential time until his next observation. And so player P can only stop at those observation times. So so I'm going to use FP for the P's payoff function. And so this can be different from FC, the payoff function for continuous player. And again, he gets this asset only if he stops earlier than player C. Okay, so this is the game. So the main objective is to form to get the Nash equilibrium. So which is the pair of a strategy such that one is a best response to the other. So so I'm going to use tau for player C strategy. And remember that so C can observe the process X in a usual way. So pretty much he can choose any stop in time, of the state process X. And okay, so this TC is a set of all stopping times of X, and C can choose any time from this set. But on the other hand, a player P can only update his information at independent Poisson arrival times. So basically, he can only choose among those stopping times, which corresponds to basically the jump times of this independent Poisson process. All right, so each player wants to maximize the expected payoff. So so let me use this capital VP as P's expected payoff function. And so this sigma is P strategy, and tau is a C strategy. And so this small x is a starting point of the process. So again, so what happens here is that so P so gets this asset, and so only if P stops earlier than player C. And so we assume a constant positive discount rate, which is Q. And so in the same way, so I'm going to define VC as the expected payoff function for C. And so for C, okay, so again, so FC is the the payoff function for player C, and he gets this asset only if he stops earlier than player P. So so what we want to obtain is again the Nash equilibrium, so which is a pair of strategies. So let's say sigma star and the tau star, so which are selected from their strategy sets. And so basically for this to be the Nash equilibrium, so for P, so given that C strategies is fixed to be tau star, so P maximizes by his expected payoff by choosing tau star. So maximization over all basically stop in time in his strategy set. And also for C, so given that P's strategy is fixed to be sigma star, then C maximizes his expected payoff by choosing tau star. Okay, so that's pretty much the classical definition of the Nash equilibrium. So that's what we want to obtain. So in this talk, so I'm going to focus on the case when the payoff function is high, when the state process X is low. So you can just think of American put options. I mean perpetual put options, and for both players. So for the case of a perpetual put options, and in many cases, the optimal strategy is of a threshold type. So in that classical formulation, basically the down crossing time is going to be optimal. So here, okay, so let's say player C follows basically the classical down crossing time. Okay, so this is going to be the first basically hitting time below A, right? So that's a very reasonable strategy, right? So in this condition. But this is not possible for player P because P can only observe the process only at exponential times. So basically the best thing he can do is to stop among his observation times, among these Poisson arrival times at which the state process happens to be below some barrier. Okay, and okay, so given this pair, right? So P should choose L higher than A. I mean, otherwise, C is going to stop before P all the time. Then basically P gets nothing all the time, right? So P should try to choose the parameter L higher than A. So I made two plots, and so this one, okay, so let me just explain. And so the process, state process X is given by, so this, trajectory, the black trajectory. And so there's another randomness, so which is about P's observation times, so which come at, exponential times. So, so what we have is that, so these vertical lines correspond to the observation times for, player P. And so what is happening is that, so this is the first observation time for player P, right? So this is the first time he can update his information. And then he updates and he observes the process X at his observation time. And so here, so this is above, so this is L, right? So the barrier for player P. And so this updated value is still higher than L. So he decides to continue. And then he waits for exponential time. And then he observed that the process is below L. So in this case, so this red circle is the time player P basically stops. But on the other hand, player C stops at the classical down crossing time. So so the first time the process X goes below this level is shown by this green square, right? So this is a time player C stops. Okay, so in this case, player P stops earlier than C, but this is not always the case. And so in this case, okay, so this is the first time P observed the asset value, okay, and then at this first observation time, he finds that the process is above his barrier, so he decides to continue. But this time, he ends up waiting for a long time until the next observation time. And then he observed that the process is below, so this, upper, this L, the barrier for player P. And then, okay, so this would be the time the player P stops. But in this case, so before that, the process X has, crossed A already. So this is going to be the time player C stops. And so this is a time player P stops. So in this case, so player C stops before player P. Okay. So in this talk, so what we want to do is to come up with cases where so this set of down crossing times, the classical down crossing time and the Poisson down crossing time become the Nash equilibrium. And so what we assume is that the first for the state process X, we assume that X is the spectrally positive Lévy process, or the Lévy process with only positive jumps. And also about the pair function F. So because player C gets more additional information, and he gets to observe more often the state process. So he has to pay some fee for the information. So that's why. So we assume that pair function for P is higher than the pair function for C. And so other assumptions is that for basically the down crossing time to be optimal, it's very natural to assume that F is a decreasing function, and so we assume some smoothness. And additionally, we assume that F is a concave function, and so we assume so these three conditions for each FP and FC. Okay, so these conditions are satisfied. For example, for put options in the Black-Scholes model where the asset value is exponential Lévy, and also in the Bachelier model as well. Okay, so what we're going to do is to use some like known results. I mean, some new techniques for the Lévy processes observed at the Poisson arrival times. So we have two kinds of down crossing time. So tau A minus is the classical hitting time. So that tau A minus is the first time the Lévy process goes below some level. And so this new stopping time is again, so this is the first Poisson arrival times at which the Lévy process at this Poisson time is below some level, okay, for the first time. So it would be nice to compute so these quantities, because what we want is to show that the Nash equilibrium is given by a pair of these strategies. Okay, so let me just define by so this small VP at the expected pair for player P. So when player C chooses A as his barrier, and the player C chooses L as his barrier, right? So okay, so so that's exactly what that is. So player P so gets this asset only if so this stopping time is before this stopping time, and we define the expected pair for C, so in the same way by BC. So so this involves some very special stopping time, and some people in insurance mathematics community have worked on the Lévy processes observed at the Poisson arrival times. So some results can be possible when the Wiener-Hall factorization is known. For example, for the case when the jumps or IID exponential or a phase type. And also, so if you focus on the case expected positive or expected negative, or the jumps are always positive or the jumps are always negative, then so we have a very nice tool called the scale function. So what we do is to first write these expectations in terms of the scale functions. Okay, so that's going to give us a very good start. So let me just review about the expected positive Lévy process and the scale functions. And so let me just start with the Laplace exponent of the process x. Okay, and x is expected positive Lévy process. So the Laplace exponent is given by the log of the Laplace transform of the Lévy process x at time 1. And so thanks to the Lévy-Khinchin representation, so this can be written in terms of the sum of 3 parts. And so this first linear part is almost the drift. And the second part is about the Brownian motion or the diffusion part. And the integral part corresponds to the jumps. So here, so pi is a Lévy measure. And because we assume the jumps are always positive, so the support is going to be the positive half line. And so in general, the Lévy process can have infinite number of jumps in a finite interval, but these jumps have to be very small. So we assume that the second moment of the Lévy measure has to be finite. And so x can have paths of boundary variation or unbounded variation. And it is of boundary variation if and only if so there is no Brownian motion. And if you take the first moment of the Lévy measure around 0, it has to be finite. And also we exclude some trivial case where x has a monotone path almost surely. So we're going to use the scale. So its definition is quite easy. So so we're going to use so WQ for the scale function. So so which is parameterized by Q. So which is the discount factor. So the scale function is given by a mapping from real number to a positive real number, and on the positive half line, so it's defined by the Laplace transform. So if you take the Laplace transform of W, it's going to be given by 1 divided by the Laplace exponent minus the discount factor Q. And so this holds for every beta larger than capital phi, so which is given by the largest solution to the equality that the Laplace exponent equals a discount factor Q. So this is often called the Kramer-Limburg equality in insurance mathematics. And it's always convenient to define so what we call the second scale function, which is basically written in terms of the first scale function. So we somehow integrate the scale function and multiply by constant and and so on. Okay, so what we can do with the scale functions are basically summarized as follows. So so let me just first start with the one-sided exit identity, so which does not even require the scale function. So suppose the process starts at this small x, which is higher than 0, and so this is the first down crossing time below 0. So you can obtain the Laplace transform of this classical down crossing time. So this is given by some exponential function where phi is again the largest solution to the equality that the Laplace exponent equals a discount factor q. All right, so if you extend from one-sided exit to two-sided exit, then we need the scale functions. So let me define, okay, tau b plus to be the first, up crossing time above b. And then, so we can obtain, so this expectation. So this corresponds to the event that, the Lévy process goes below 0 before going above b. And you also discount. So this can be written as the fraction of the scale function, w. And for the other event, so if you think about the event that the process goes above b before going below 0, but in that case, it's a little bit complicated because we assume that the process x has positive jumps. And it can happen that the process can jump over the up crossing time. And so there might be an overshoot. Okay, so so this is going to be the overshoot, and so we can obtain the joint Laplace transform of this up crossing time and the overshoot. So with this condition, and so this can be written in terms of the first scale function and the second scale function. And also another important application of the scale function is for the resolvents or potential. So if you want to compute the running payoff or running cost, so okay, so this quantity, okay, running cost, running payoff accumulated until the first time the process goes above b or going below a, admits a density, and the density is given by the scale function. Okay, so these results can be found in textbooks, and but what we need is something more advanced. So now, okay, so we need some okay, so we have to introduce the Poisson observation times, right? So, and for that, so let me just define like one additional function, which is given by some gamma. And so this is basically some sort of the convolution between FP. So FP was a pair function for player P, and the scale function W. So now using so this function gamma and the second scale function z. So we can write so player P's expected payoff again. So player P, okay. So player P chooses the Poisson down crossing time, and player C chooses the classical down crossing time. Okay, so so this expected value corresponding to a pair of these strategies can be written in terms of, okay, so z and this guy. Okay, and in particular, when the starting point on x is smaller than a, so a is a C's barrier. So in that case, if it starts at x smaller than C's barrier, then C is going to stop right away. So I mean, there's no chance that the P can do anything. So in that case, so P's P's expected value is going to be 0. And for player C, it's going to be a bit more simple. So C's expected payoff for the same set of strategies can be written in terms of the second scale function. And Okay, so again, so when the starting point is below A, then C stops right away. And so this is going to be C's expected volume. Okay, so now let me just move back to the problem. And so let me just tackle the problem in 2 steps. The first, we suppose that the strategies are restricted to be of a threshold type. So we just impose each player to follow the threshold type strategy. Well, in that case, so basically each player wants to choose the barrier A and L. And so what we want is a natural equilibrium. So the pair of A and L, such that player P chooses L star. So given that C chooses A star. And the same way, player C maximizes by choosing A star, when player P chooses L star. Okay, so this is basically the first result, and then we're going to strengthen the results because this is sort of like naive version of the equilibrium. Okay, so let me just remind you about other assumptions. So we assume that the state process X is expected positive the Lévy process. And we assume that the reward functions FP and FC have to satisfy these properties. So again, pair function for P should be higher than the pair function for C, and both functions are assumed to be decreasing, differentiable, and concave. Okay, so now we focus on this game, right? And what we should do is quite simple, because we just want to maximize over one parameter L and A. So so why don't we just take the first order condition. Okay, so for P, so P wants to choose the best L. Okay, so let's just take the partial derivative of this guy with respect to L. And so what you get is something you would expect. So you take the partial derivative, so this becomes the product of some term which can be shown to be always positive, and some term which does not depend on the initial value X. So if you have worked on the stochastic control for the Lévy processes, because the Lévy process is homogeneous spatially, so the optimal barrier is usually independent of the starting point of the process. So this is exactly what we get. So this is always positive, so we can just ignore. And so what we want to do is to choose L such that so this term becomes 0. So in the same way, so let's do for player C. So we differentiate his expected payoff by A. And again, so we get that, so it becomes a product of some term which is always positive, and some term which does not depend on the initial value of the process. Okay, so so this shows you which L and which A so we should choose. Okay, so let me just sort of summarize. So if player C chooses A, okay, so the best response for player P is to choose some level L, which is sort of the function of the opponent's strategy A. And so this should be such that the first order condition is satisfied, which is nothing but the condition that, so this term becomes 0. And so in the same way, so if player P chooses L, then the best response for player C is to choose some level A, so which is a function of the opponent's strategy L, such that the first order condition, so which is this guy, is satisfied. But here, so we have to make sure that so this function makes sense in that so these equations have solutions, and for these to be functions, okay, one-to-one. So we want to make sure that so these attain a unique solution, right? So we could confirm that. So this is so. So these functions are well defined, and then the next step is to basically find a pair of A and L, such that so these are basically the best response to each other. So basically we were able to construct analytically, explicitly the pair, like one pair, such that so these hold at the same time. And since so these are chosen so that the first order condition is satisfied, so this satisfy that these equalities, right? So this is pretty much what we wanted to show, and the pair of L star and A star so become a natural equilibrium. So we could obtain like one of a pair such that so these are satisfied, and we spend like a lot of time if the one we obtained is the only solution, but I mean we couldn't quite do so. So these may not be unique. So there might be like more than one the Nash equilibrium. So we were not so happy with that, so we just tried to do a bit more. So basically, so the one we obtained is so basically the smallest one among all the Nash equilibrium. So in that sense that so L star, the player P's barrier is the smallest. And so we can basically show that the one we chose is basically the best, so the best one. So in that, so this is a Pareto superior to any other Nash equilibrium. So in that, so basically this means that the expected payoff for each player is higher. Okay, so that's what we call the Pareto superior. Okay, so we have shown that okay, so this weak version of the equilibrium, and but that was not our final goal, and because we just focus on the threshold strategy, so which may be acceptable in economics, but maybe not in mathematics. So we want to upgrade to the original natural equilibrium, right? So we want to, we should not focus on the set of threshold strategies. Instead, we should allow these players to choose any stopping time in their strategy set. So to upgrade from so this to so this one. So basically what we have to show is so this, right? So so basically this is the verification step in a stochastic control, meaning that the candidate value function we obtain is indeed optimal in terms of this one, right? So here we focus on the set of strategies to be a threshold type. And so we want to show that, even if you expand, even if you allow player P to choose any strategy in his strategy set, okay, the bear strategy is indeed the best better. So basically, we have to verify the optimality for player P and player C. So we have to solve the two optimal solving problems for P and C. So let me just do that. So for player P, so the verification was not so bad. So for player P's problem is a bit unusual because he can only stop at the Poisson arrival times. But it's quite easy to come up with sufficient condition in terms of the generator L and some inequalities between the value function and the pivot function. So we can show the smoothness. So basically, VP is smooth enough so that this generator term makes sense. And so I remember like one of the items was quite difficult, but we were able to show each item, and so basically, so this shows that our candidate value functions is indeed optimal. So what was very difficult was the verification for player C. So we tried the classical verification argument. But we ended up spending lots of time and we failed. But luckily we found some paper which they call the average problem approach. And in particular, we were able to use the paper by Long and Zhang. Okay, so to do that, so basically we first have to convert the problem. Right. So remember for player C. So given that the player P strategy is given by the the Poisson first Poisson down crossing time. So what happens is that whenever the state process is below P's barrier, then at the rate lambda, so the opponent exercises, then C loses opportunity. So we can just, take so this risk in the discount factor, so which is quite an easy trick. So we can just, first convert the problem to a usual optimal stopping problem, where so discount factor is, basically given by this additional occupation time. And so let me just explain about this average problem approach by Long and Zhang. And so they focus on the case of expected negative process. So let me just use Y as the state process for them, so which is expected negative Lévy process. And so let's say Y bar is a running Spearman process. So they worked on the case of the stochastic so discount rate. And so what it did is to define some left inverse of this additive process. And as the first time, so this process exceeds some independent exponential time. And so they define as the historical maximum until so this random time at the lifetime, and then they computed its hazard rate, which give us follows. And using the hazard rate, and they somehow managed to show that, so if you define some function H hat, which is written in terms of this hazard rate. And so if this function attains a unique root, so then this barrier strategy using the root as a barrier is indeed optimal. So we could just use the result directly, and because we focus on the cases of spectrally positive, they work on the spectrally negative. We first have to flip the processes, and we just follow the same steps, and it turned out that this key function h hat can be written in terms of some function j divided by some positive function. And so this j function is something you saw earlier. So basically, so j equals 0 is exactly the first order condition. And so basically we chose a star such that, so basically this thing vanishes. So we could just use so this paper and to show that, okay, so player C indeed optimizes over all his strategies. Okay, so let me just conclude in a few minutes with some numerical results. So here, let me focus on the case of put options. So okay, and okay, so remember that the P's payoff function is higher than C's payoff function. So strike for P should be higher than strike for C. And I mean, it's not so important, but we just use some simple Lévy process with jumps which are given by IID exponential random variables. And let me just skip this, but basically we could obtain a pair of barriers, so which basically satisfy the two first order conditions, which was quite easy to do. And so this is how the volume function looks like. So for this is for continuous player C, and so this is for periodic player P. So player C, so C's the volume functions tends to be, okay, it's pretty much what we see for put option problem. So we get some very nice curve which is convex and very smooth. And I don't know if you can see, but there's a star. So this is C's barrier, C's optimal barrier, a star. And so this vertical line shows you the L star, or the barrier or the barrier of player P. All right, to confirm the optimality, we just tested, and what happens when player C choosing a wrong selection of A. Then so these are shown by these dotted lines. So these are indeed dominated by this volume function. And what's more interesting is the volume function for player P. So what happens here is that so A star C's barrier is given here. So this around here. So when the starting point is below A star, so then player C stops right away. So player P's the volume function is 0. And then at A star, it starts to increase and then decrease. So that's how the volume function for P looks like. And also to confirm the optimality, we just compare that for wrong selections of L, which are given by these blue lines, and we can confirm that so the volume functions is indeed okay, optimal. And so we tested against the lambda. So lambda is the observation rate for a player P. And what happens is that, so this is, how it changed, how the volume function for player C changes. So as lambda increases, the opponent basically gets stronger. So his volume function tends to, decrease. Right, so this is something we expect. But for player P, so P's volume function, right? So even though he gets stronger as the lambda increases, but we don't see monotonicity because of this ugly behaviors here, right? So what is happening is that so basically when lambda is low, then player C does not need to hurry up, so he can just set his barrier to be some low volume. But as lambda increases, then the player C has to stop earlier by choosing higher A star. So that's why it moves like this way. Okay, and then go up and down. Right. So okay, so maybe around here when the starting point is high, then player P has advantage or high value of lambda, but it's not always the case. I mean, depending on the the starting point of the process. And so we also plotted these two barriers, L star and A star. Okay, so basically they tend to the distance between L star and A star tend to shrink, but so it's not going to go to 0. And so here, like 50 is the strike price for player C. So it never exceeds the value 50. And so they don't go to the same values. So that is because even when the lambda is very high, if they try to stop at the same time, player C always has that priority to stop earlier. So that's why even when lambda is super high, the information is not symmetric. Okay, the last thing we want to show you is about how to quantify the volume of information. Okay, so we just define the value of additional information to be the amount of fee player C has to pay, right? So it's pretty much the difference between the two strikes, so that it's going to be fair in that the value function coincides. So this of course depends on the initial value of the process X, and also with respect to the rate of observation lambda. So here's a plot of delta, okay, against the initial value. And so basically what happens is that I start at 60. So 60 is KP, because when it starts as a very small number, then C is going to stop right away. So of course, the difference is going to be 60, and then tends to decrease. And so with respect to lambda, so when lambda is super low, right? So then player C has so much advantage, so he should pay more fee. So it starts as some big number, and basically as lambda increases, it should tends to decrease. But it turned out that it's not gonna go to 0 exactly. So that is because, again, even when lambda is very high, player C always has advantage to stop earlier if they try to stop at the same time. Okay, so it's not going to be 0. Okay, so I just listed 4 important papers, and the first paper is maybe the most well-known paper on the Lévy processes observed at the Poisson arrival times. And the second paper, so this is a book chapter. So this is gives you a very good review about the scale functions. And this third paper is the one we used for the verification for player C, and so this is extension of so this paper. Okay, so thank you very much for your attention.